Welcome to Brain Vision.
We have a simple Rankine cycle that uses water as the working fluid. The boiler operates at 6 megapascals. So P2 and P3 are 6 megapascals. Let's see, the condenser operates at 50 kilopascals. And the temperature of the steam going into the turbine is 450 degrees C. The turbine has an efficiency of 94%, and we can let's see here. We're told that the water leaves the condenser is supercooled by 6.3 degrees C, and the boiler is sized for a mass flow rate of 20 kilograms per second. So let's see here. We can get the enthalpy at 1 and the specific volume at 1. So again, we can get the work that goes into the pump, and it's assumed to be 100% efficient. So this is isentropic. With that, we can get the enthalpy at 2. We can then get the enthalpy and the entropy at 3, because we know these two properties. And then we can get the adiabatic entropy at 4, because by assuming that the adiabatic entropy at 4 is the entropy at 3, so the adiabatic, we're in the two-phase region. So we have let's see here, we have a quality factor of 86.6%, and H4 prime is 2,336.4. So that would be we're here. Now we're actually here, so we know the efficiency of the turbine. So that allows us to figure out what H4 is, and that is 2,394.4 kilojoules per kilogram. With all these properties, the thermodynamic properties, we can figure out what the work put into the boiler is, and that is about 60 megawatts. We can also figure out the work coming out of the turbine that would happen here, and that is about 18 megawatts. The work going in to the pump is 122 kilowatts. So the net is roughly 18 megawatts. Again, this is usually very small compared to that. We can then find the thermodynamic efficiency by taking the net work, or the net power, divided by the net heat flow in, and that winds up being about 30.25%.